overrepresented sequences. What is this telling you? This is a table, and this tells you what the duplicates are. So what is he doing? He is taking all the reads that are occurring a lot in your FASTQ file. So more than 0.1% of your FASTQ file. He's taking these reads and he's blasting them against a database of known contaminants. What are known contaminants? Well, typically adapter sequences. So during the library prep, there is always a step where you're going to ligate adapters to your fragments. But ligation, you have no control over it, so you will also ligate adapters to each other. And they will also appear as fragments in your library. You can sequence them, but what you will sequence in that case is adapter dimers, adapter sequences, and not fragments. So, but they will appear in your library. So since they are known to contaminate most next-gen sequencing libraries, FastQC is blasting these reads against a database of adapter sequences. It will give you an overview of all the sequences, all the reads that occur a lot. You can see here how much they make up in your FastQ file. Here you see the absolute number. So the first sequence occurs more than 1 million times, 1.8 million times in your FastQ file. And then here in this column, you see the result of the blast. If you want to know the sequences of all the contaminants that he is checking, you can take a look in the documentation. So these are all the sequences of all the adapters here that are being checked by FastQC. So normally, if you don't do an exotic experiment, your adapter should be here. If you have very special adapters, specially made for you, then you can also give FastQC a list of the adapters that you expect to be in your experiment, and then he can take this in as a blast database instead of the built-in one. So you can specify one yourself. So if you have contamination in your libraries, in 99% of the cases, it will be adapter dimers. Sometimes it's other stuff. What can it also be? It could also be this one, Phi-X virus sequences. Where do they come from? Well, your sequence provider will add them to your libraries when you work with an organism with a very exotic GC content, like Arabidopsis or Plasmodium or bacteria. Why? It has to do with the calibration of the sequencer. So the first 10 cycles of the sequencing, the sequencer is still calibrating. And for calibration, he needs to have a random choice between an A, a T, a C, or a G. Yeah? So if you have organisms with a very extreme GC content, that's not the case. Yeah? Then you will have more chance of having an AT than a GC or vice versa. So to make the calibration right, your sequence provider will add these sequences so that they improve the GC content to a normal GC content and the calibration is done in a right way. And the same is true for libraries which are very small, which have the same fragment thousands of times. So also there, if you have the same fragment thousands of times, it will influence, it will not be random. So the calibration again will be bad. So he has to add them. So you might also see these as contaminants in your libraries. When you have DNA-seq data, you might see repeats as contaminants. When you have RNA-seq data, you might see your ribosomal RNAs as contaminants. If you want to know what is contaminating your library, again, the best thing that you can do is simply blast the sequence yourself.